Hey everyone, welcome back to Tech University Tutorials, the channel where we make complex computer science topics simple, fun, and easy to understand. I'm so glad you're here today because we are diving deep into one of the most important topics in information security, SHA-1, the secure hash algorithm. If you ever wondered how your password are protected, how GIT tracks you, code, or how website verify your downloads, SHA-1 is at the heart of all of that. And by the end of this video, you'll understand exactly how it works. So make sure you hit that subscribe button right now if you're new here. Let's get into it. Before we talk about SHA-1 specifically, we need to understand what a hash function is, because SHA-1 is one type of hash function. So here's a simple idea. Look at this diagram on screen. You take any input, let's say the text hello world, you pass it through SHA-1, and what comes out the other side is a fixed length string of characters. That string is called a hash or digest. No matter how big your input is, whether it's a single word or a 100 gigabyte file, SHA-1 will always produce the same size output, 160 bits, which is 40 hexadecimal characters. Now let's look at the 6 key properties of any good hash function. Number 1, deterministic. The same input always gives the exact same hash, every single time. No randomness. Number 2, one way. This is critical. You can go from input to hash, but you cannot go backwards. You cannot take the hash and figure out the original input. It's a one-way street. Number 3, avalanche effect. This is my favorite. If you change just one tiny character in the input, even one letter, the hash output changes completely. It looks totally different. Number 4, fixed output. SHA-1 always gives 160 bits. Always doesn't matter if the input is one letter or 1 million. Number 5, collision resistance. It should be nearly impossible to find 2 different inputs that produce the same hash. We'll come back to this when we talk about SHA-1's weakness. And number 6, efficient. The hash can be computed quickly, even for very large amounts of data. All right, now we understand hash functions. Let's look at where SHA-1 came from. SHA-1 has a fascinating history. Let me walk you through the timeline. Back in 1993, the NSA, the National Security Agency, designed a hash function called SHA-0, and NIST published it as a standard. But there was a problem. A cryptographic flaw was found almost immediately. So 2 years later, in 1995, the NSA revised SHA-0 and released SHA-1. This became FIPS Pub 180-1, a federal information processing standard, and SHA-1 quickly became the most widely used hash algorithm in the world. Then in 2005, researchers started finding weaknesses. Cryptanalysts showed that SHA-1 collisions could be found much faster than expected. This raised serious security concerns. By 2011, NIST officially recommended moving away from SHA-1. Browsers and certificate authorities started phasing it out. And then in 2017, the big moment, Google and researchers from CWIN, Amsterdam pulled off the SHA attack. They produced the very first real SHA-1 collision. 2 completely different PDF files that had the exact same SHA-1 hash. That was the final nail in the coffin for SHA-1 in security applications. Now you can see on the right side of the slide, SHA-1 was used in SO, many systems, SSL certificates, GIT, PGP email encryption, digital signatures, and code signing. That's why understanding it still matters. Today, it's everywhere in legacy systems. All right, now let's get into the actual mechanics. How does SHA-1 work? Internally, there are 5 main steps. Step ONE, message padding. Before SHA-1 can process your message, it needs to pad it to the right size. It adds a 1 bit at the end of your message, then adds zeros, then adds the original message length as a 64-bit number. The result must be a length that is 448 mod 512. This ensures the message fits perfectly into 512-bit blocks. Step TWO, parse into blocks. The padded message is split into 512-bit blocks. Each block is made up of 16 words, where each word is 32 bits. Step 3. Initialize hash values. SHA-1 start with 5 fixed constants, H0 through H4. You can see them at the bottom of the slide. These are predefined magic numbers that come from the algorithm's design. They form the initial state. Step 4. 80 rounds of compression. Each 512-bit block is processed through 80 rounds of compression function. This is the heart of SHA-1. We'll look at this more closely in the next slide. Step 5. Output the 160-bit digest. After all blocks are processed, the final values of H0 through H4 are concatenated together. 5 32-bit values gives us 160 bits total, which is your final SHA-1 hash. Now let's zoom into step 4, the 80 rounds. This is where the real magic happens inside SHA-1. The 80 rounds are divided into 4 groups of 20 rounds each. Round 0 to 19 use a function called CH. The choose function. It picks bits from C or D depending on the value of B. The constant use here is 5A827999 in hexadecimal. Rounds 20 to 39 use a parity function. It XORs B, C, and D together. The constant is 6ED9EBA1. Rounds 40 to 59 use a majority function. A bit is 1 if at least 2 out of the 3 inputs B, C, D are 1. Constant is 8F1 BBCBC. Rounds 60 to 79 go back to parity again, but with a different constant, CA62C1D6. And at the bottom of the slide, you can see the general formula for each round. T equals IOTL5 of A, plus the function result, plus E, plus the message, word weight, plus the constant KT. Then all 5 registers are through E shift. This repeated mixing, shifting, and combining is what makes SHA-1 produce such dramatically different outputs for slightly different inputs. Let's now look at SHA-1 in real action with actual examples. Here you can see 4 inputs and their real SHA-1 hash outputs. The word hello gives a hash starting with F7FF9E8B. Now look at hello, lowercase h, and the hash is completely different, starting with A4C61D, not even close to the first one. Then hello with an exclamation mark, again, totally different hash. And finally, an empty string, SHA-1 of nothing, still gives a valid 160-bit hash, DA39A3E. This is the avalanche effect in action. We change just ONE character from capital H to lowercase h, and the entire hash output flipped. This is what makes hash functions powerful for detecting any change in data. If even 1 byte changes in a file, the hash is completely different. That's how file integrity checking works. Now let's talk about why SHA-1 is no longer considered secure. For critical applications. On the left, the strengths. SHA-1's 160-bit output was considered very strong back in 1995. It's fast and efficient to compute. It was standardized globally and worked reliably for over 20 years. And it's still perfectly fine for non-security users like checksums. But on the right, the serious weaknesses. The biggest problem is collision attacks. Researchers found that SHA-1 collision could be found much faster than the expected brute force. Difficulty of 2 to the power 80 operations. And then in 2017, the shattered attack showed a real collision. 2 different PDF files with identical SHA-1 hashes. This is devastating. For a cryptographic hash function, NIST deprecated SHA-1 for use in digital signatures. Today, browsers reject any SSL certificate signed with SHA-1. So the lesson here is SHA-1 was great for its time, but cryptography evolves. Always use modern standards for security-critical systems. So if we can't use SHA-1, what should we use? Let's compare the full SHA family. SHA-1 gives 160 bits output, uses 512-bit blocks, runs 80 rounds. Was released in 1995 and is today deprecated, not for security use. SHA-256, which is part of the SHA-2 family, gives 256 bits output. Same 512-bit block size, but only 64 rounds. Released in 2001. This is currently the recommended standard for most security applications. Your HTTPS connection right now likely uses SHA 256. SHA 3, based on a completely different design called KEKAC, gives up to 512 bits output, uses much larger internal state in a different sponge construction, released in 2015. This is the most secure today, recommended for highly critical applications. The takeaway: SHA-1 is dead for security. Use SHA 256 for general security. Use SHA-3 for the highest security requirements. Even though SHA-1 is deprecated, it's still used in many real-world systems, especially legacy ones. Let's look at the 6 key applications. GIT version control. This one still uses SHA-1 today. Every commit in GIT gets a SHA-1 hash as its unique identifier. When you do GIT log and see those long strings of characters, those are SHA-1 hashes. GIT is working on moving to SHA 256, but SHA-1 is still the default. SSL TLS certificates. Historically, SHA-1 was used to sign HTTPS certificates. Browsers now reject SHA-1 certificates, so all websites must use SHA 256 or higher. PGP and email signing. SHA-1 was used to digitally sign emails and verify the sender. This proves the message wasn't tampered with. File integrity checks. Software downloads used to include SHA-1. Checksums. You download a file and run SHA-1 to verify it wasn't corrupted. Today, SHA 256 is preferred, but some older tools still use SHA-1. Code signing. Developers used SHA-1 to sign software packages, now replaced with SHA 256 in modern systems. HMAC SHA-1. This is still used today. HMAC, which stands for Hash-Based Message Authentication Code. Using SHA-1 is still acceptable in some contexts like OAuth 1.0 and certain API authentication systems. So SHA-1 isn't completely gone, but you need to know where it's safe and where it absolutely must be replaced. Alright, let's wrap up with the 5 key takeaways from today's lecture. Takeaway 1. SHA-1 produces a 160-bit hash. It takes any input and always gives you a fixed 40-character hexadecimal output, deterministic and fast. Takeaway 2. SHA-1 has 5 steps. Pad the message, parse into 512-bit blocks, initialize 5 hash constants, run 80 rounds of compression, and output the final 160-bit digest. Takeaway 3. It's one way with a powerful avalanche effect. You can't reverse a hash, and even a 1-bit change in input completely changes the output. Takeaway 4. SHA-1 is deprecated for security. Don't use it for digital signatures or certificates, but it's still present in GIT, HMAC, and many legacy systems, so you absolutely need to know it. Takeaway 5. Upgrade to SHA 256 or SHA-3 for all new security applications. These are stronger, current, and NIST recommended. And that's it for today's lecture on SHA-1. I hope this was clear and easy to follow. If you learned something new today, please like this video. It helps the channel grow more than you know. Subscribe to Tech University Tutorials for more information security lectures, and share this with your classmates who are studying for their exams. Drop a comment below. Tell me, what topic should we cover next? Thank you so much for watching. See you in the next lecture. Peace.